Hello everybody and welcome to the Carlin Cymru revision sessions. This session this evening will focus on AS Pure Maths, and Mr Mackenzie and both core will be going through modelling, exponentials and transformations of curves. The session will last around 45 minutes and Mr Mackenzie will go through some questions. If you have any questions during the session, please use the Q&A section on the right and we'll do our best to answer you. And I'll shortly be putting a hyperlink in the Q&A section. So if you're happy to leave your name and email address, we would love to keep in touch with you so we can send you information about future events. You can click on that link anytime during the session. Today's session and all of the previous ones have been recorded, and the recordings and any relevant resources are uploaded onto the e-sgol website under the Carlin Cymru tab. Thank you, Mr Mackenzie. Over to you.
Thank you, Mr Weatherhead. So yes, I know it says numerical analysis at the top. That's from a previous PowerPoint. When this goes up, I'll sort of delete that. So I'm going to look at exponentials today, modeling, differentiating with them, and then the back end will be transformation of curves. With regards to exponentials, I think it's important that you see what the sketch of it looks like. So the one in green is your y equals e to the x. Now e to the x is a natural number. And then you've got the inverse of e to the x as, if we were to sort of draw the line here of y equals x, that's y equals x. A reflection of that would be this red line here, and is the inverse of e to the x, and this was y equals ln of x. So on your calculator, you will see in sort of white writing the ln x, and then above it, and you'd have to press shift, will be e to the x. So those two are directly linked. Other sort of logs are on there and are used throughout, but this one is a special one. I'll show you in the next slide. I want to also sort of make sure that you're aware that this cuts because of the fact that x is 0 on the y-axis. If you put e to the x or e to the 0 in, you will get 1. So this cuts here at 1. Again, because it's reflected, this will be here at 1 as well. They have asked in the advanced knowledge that you're able to sketch and understand the inverse of these functions. I'd also like to sketch in, let's go purple, sketch, let's see, y equals e to the minus x. This also can be written as 1 over e to the x, because as we know with index numbers, if it's a minus number, you can flip it and put it underneath. So this will come from over this side, and we'll go down, we'll cross, and we'll look and keep on going. So the asymptotes of these, so this is y equals e to the minus x. It also will ask you to write down the asymptotes. So the asymptotes are the x and the y axes. It's important because if you were then, I don't know, said sketch y equals e to the x and then separate plus 2, when we do transformation of curves, you'll see that that is then shifting or translating along the y-axis by 2. So then the asymptote will be at 2, y equals 2. Okay, so it's important that you understand and that you know where these graphs come from. And what was the next one? So the next then is differentiating e to the power x. Now, the WJC in its advanced knowledge has said that y equals e to the x differentiates, or the gradient function for it is e to the x. I would like to show you where that comes from. Okay, so the reason why it's special, if another exponential would be y equals 2 to the x. So anything with a number base, or whatever you want to call it, to the power of x, that's what we'd class as an exponential. And again, the graph of this would look, that's hideous. That would get sort of, you would be reduced mark because of the fact it should tend towards it. So you would have to then make sure that when you put it in so that it tends towards and not comes back on itself, or even, in fact, touching the line. Do it from here. So this would be y equals 2 to the x, and that would be 1. So if I was to differentiate this, y by the x, it would be 2x ln 2. So you have an extra ln of 2. And again, if you were to differentiate 3 to the x, which is another exponential, it would be the same. So the reason why we found this quite powerful is because y equals e to the x, the differential of which is e to the x ln of e. Well, ln of e is equal to 1 because they're inverse of each other. So then you have y equals e to the x goes differential or differentiates to e to the x, which is the gradient function, or in this case, especially when we're going to do the modeling question, would be the rate of change. Okay, that's important that you know that is going to be the rate of change. And I also wanted to go through very quickly the chain rule, because it's all the WJC have said in the advanced knowledge that you need to differentiate e to the kx. I'd like you to see where it comes from. It's not like when you don't need to understand it. It's more you'll do this in A2, but I think it's important that you understand where it comes from. So the chain rule is a form of differentiation where it is a function inside a function. So function inside a function. We have y equals, if I put e to the 5x. So how it works is the chain rule is dy by dx equals dy by du times du by dx. With what we do is we substitute in the function that's inside the function. So we would have y equals e to the u, and we would have u equals 5x. So then we'll differentiate this with respect to u, and that just creates its own thing, e to the u, and then we differentiate this, and this 5. So then we put the numbers back into the chain rule. We have dy by dx, so that is dy by du, so that's e to the u, times du by dx. That little dot there is times. So it's going to be 5e to the u, which is going to be 5e to what u was, which is 5x. And you can have a go at doing some of these yourself. We can also make it a little bit quicker. So if we had y equals e to the minus 7x, if we differentiate, let me sort of, if we differentiate this, then that's going to be minus 7. And then if we differentiate the function itself, which is e, then it just goes e to the minus 7x. So dy by dx equals minus 7e to the minus 7x. We don't need to worry about log of e and all the rest of it because we know that just goes. Okay, so that's a little bit about the chain rule, but you will do the chain rule, product and quotient rule more in A2 rather than in this. But I wanted you to understand where it's coming from so that way you can then work through it yourself. The next one I wanted to go on is solving. Okay, it's important that you know how to solve. You've done and covered logs. So this is solving e to the x. Here we have solve 3 equals 2e to the 0.5x. It's vitally important that you know how to do this, especially with the modeling sort of questions that I'm going to do after this. So I'll do this one, and then I've got another one I want you to sort of, we'll work through, and then we'll go from there. So you need to get e to the 0.5x on its own, first of all. So you would take the 2 over to the other side, so it's going to become divide. So I would write it as e to the 0.5x equals 3 over 2. Now we need to get rid of the exponential, or the e in this case, so that you can have 0.5x on its own. Well, like we did before, if we take ln of both sides, now it's important that you don't take logs of both sides, as in log to the base of something else. It has to be natural log, which would be ln. So if we take ln of both sides, we get ln e to the 0.5x, and that is equal to ln 3 over 2. And since ln of e to the 0.5x, that'll just be 0.5x. Ln of, let's put it as 1.5. Then it's just a case of you can either times both sides by 2, so that would be 2 ln 1.5, or you can work out ln 1.5 on your calculator and divide by 0.5. It really doesn't make any difference. I prefer to do 2 ln of 1.5, put that into your calculator, and then it comes out as, to 2 decimal places, 0.81. Now, as Mr. Weatherhead and myself have said, throughout the whole series, these are online and will be on the Carlin Cymru website. So if you want to go back over something, you can, or if you want to pause the video and maybe have a go at doing one yourself, then that's fine as well. The next question, question 2, solve for x. So it's e to the 2x plus 1, and that equals 73. So you can pause here and then you can work your way through it and then see the answer at the end. There is other sort of pure videos on the AS website, and we're building up a full sort of catalog. So if there are other things you'd want to go through, then you can maybe look at them there as well as other subjects. So here, again, I would take ln of both sides. Take ln of both sides. So you can even just do then 2x plus 1 equals ln of 73. Move the 1 over to the other side, so that 2x equals ln of 73 minus 1, x equals ln of 73 minus 1 all over 2. Then that would give you an answer of 1.65 to 2 decimal places again. Okay, so now the modeling element thing. Okay, there's quite a lot. I've got 2 modeling questions that I'd like to go through with you, and then, as I said, I'll sort of go over then transformation of curves, which was off the course last year, but is definitely on the course this year. Okay, so there's a fair amount of writing with these modeling questions. So we have to take everything in and be aware of the phrases that they use. So the question is, a pan of water is heated until it reaches 100 degrees centigrade. Once the water reaches 100 degrees C, the heat is switched off and the temperature T of the water decreases. The temperature of the water is modeled by the equation T equals 25 plus AE to the minus KT. So the reason why we use exponentials is for growth or decay. So in this example, the decay is the temperature of the water being decreased. You could have a growth, for example, in biology, if you think of pairs of rabbits breeding, they would exponentially increase unless there was a predator around to kill them off. So it is important that you understand the reason why we got the minus KT there is because it is decay. Now, in some questions, you might have just KT, so that when you work it out, it becomes a minus, so you can see that it is actually decay. So T is the time in minutes after the heat is switched off. That's important. So T is the time in minutes after the heat is switched off. And A and K are positive constants. First part of the question is write down the value of A. Well, this sort of phrase is really important here to help us work that out. So we need to know that when T is equal to 0, that's the time in which the heat is switched off. We also know that the temperature, T, is equal to 100. Now, I'm not a big fan of putting in units into equations until at the very end I need to. So it's just going to be 100, but it is degrees centigrade. So if we put that information in, we have 100 equals 25, I label it as I, plus AE to the minus K times 0. Well, K times 0 is just going to be 0, and E to the power of 0 is equal to 1. So we end up with 100 equals 25 plus A. Rearrange that. A is equal to 75 degrees centigrade. Then for part 2, it asks you to explain what the value of 25 represents in the equation. T equals 25 plus AE minus KT. So what could the 25 be? So the 25 is separate, so that's going to be your starting value or the expected value that the temperature would go to. So it's the room temperature or the ambient temperature of the water. Room temp of the water in saucepan. Three. Right, so we've done those two, tick, tick. Now then, here. When the heat is switched off, the initial rate, and that's the important thing, rate. The initial rate of decrease of the temperature of the water is 15 degrees centigrade per minute. And again, that's also important, those units there, because it is saying to you that the rate of change, which is change in the temperature over the change in time, which if you think, if I put it down here as number 3, dT by dt, we can also write that. So it basically means we need to differentiate it. And we'll come back to then, once we've got the rate, so I need to differentiate this here. So we have equals, the 25 is going to go, because that's a normal number, and in differentiation that'll go. And then you got plus AE to the minus KT. Well, like we did with the previous examples, so we differentiate minus KT, so that's going to go to minus K. So we'll have A times minus K, put the minus there. And then that'll be E to the minus KT. But we already know what A is. We want to work out what K is. So if we put A is equal to 75 in, we have our rate of change as minus 75 K E to the minus KT. So let's go back. The initial rate, well, that's when the time T is equal to 0. The rate is going to be, it decreases, so it's going to be minus 15. So our D, the rate, which is the dt by little t, so the change in the temperature over the change in time. So if we put that into the formula, we have 75K minus 75K e to the minus k times 0, because that's the initial rate again, equals minus 15. The minuses go, e to the naught, so we have 75K equals 15, so K equals 15 over 75, which is equal to 1/5. So now we've got that, we can write down, stick a line for the next part, we can write down that T equals 25 plus 75 e to the minus 1/5 T. And as I said, what they could have done there is they could have put that K was a constant, would still worked out as if this would have been, instead of this being minus 75, would have been 75, and then take it over, it would have been minus 1/5, and then you would have plugged it in there. So it wouldn't have made any difference if they write it as K or minus KT. Then it asks us, find the time taken for the temperature of the water to drop from 100 to 45 degrees centigrade. So we have, we're looking for little t. We know that the temperature is 45, so we plug that into the equation. So we have 45, I'll put that as number 4, 45 equals 25 plus 75 e to the minus 1/5 t. In rearranging this, the 25 will go over, so that's going to go as minus 25, so that'll be 20, and then you drop the 75 underneath, so that we have e to the minus 1/5 t is equal to 20 over 75. So now we need to solve this so that we can work out the t. So it comes back to the first couple of slides where we were looking to solve exponentials. So take logs of both sides, take ln of both sides, more importantly, of both sides, so that we get ln, again, instead of rewriting it as ln, I'll just put it as the value. So it would be minus 1/5 t equals ln of 20 over 75. So t equals minus 5 times ln of 20 over 75, which is equal to 6.6 minutes. So it would take the pan of water when it was switched off 6.6 minutes to go from 100 degrees C to 45 degrees C. And then the last question is part 5. A second pan of water is heated, but the heat is turned off when the water temperature is less than 100 degrees C. Suggest how the equation for the temperature water cools would be modified by this. Well, then you're going to have to decrease the value of A, decrease the value of A, and then you're done as a modeling question. Now, as I said, if you want to, the next one, if you want to sort of work through it yourself, you can pause the video and then we'll go through it. So the value of a car, V pounds, can be modeled by the equation V equals 15,700 e to the minus 0.25 t plus 2,300, where t has to be greater than 0. Where the age of the car is in t years. Using this model, part A, find the initial value of the car. So if we want to find the initial value of the car, that's when the car was brand new. So t is going to be equal to 0. So for part A, put t equal to 0 and substitute it in. So the value is 15,700, and that would be e to the power of 0 plus 2,300. Well, anything to the power of 0 is equal to 1. So the value is 19. The value is going to be 19,000 pounds. So that's the initial value of the car. That's part A done. Given the model predicts the value of the car is decreasing at a rate, there's our rate again. So it's decreasing at a rate of £500 per year at the instant when the time is equal to large T. Show that that is the case. So it's the same thing. Our rate is the change in V over the change in T. So the change in value of the change in time. So it is dV by dt. So if we have a look at our sort of equation here, I'll put it down. So V equals 15700 e to the minus 0.25 t, and that's plus 2,300. So again, we'll do dV by dt. The constant 2,300 will just go, and then it is going to be differentiate minus 0.25 t, so that's going to be minus 0.25, and then it will be times 15,700, and then it'll be e to the minus 0.25 t. So it is minus 0.25 times 15,700, across there for times, e to the minus 0.25 t, and so that's dV by dt. That will equal, sorry, there you go, minus 3,925 e to the minus 0.25 t. So now this is my rate. We're told that the value of the car is decreasing at a rate of £500 per year at the instant when t is equal to t, little t is equal to capital T. So when we have t equals t, dv by dt is equal to minus 500, again because it is a decreasing rate. So we would put these figures into, line across here, then that's enough space. Then we would put these figures into dv by dt, so that's going to be minus 500 equals minus 3925 e to the minus 0.25 capital T. And then we now need to sort of work through these. So what we're trying to do, take the minus sign outside. So what we're trying to do is show that that is the case, which we have done. And then so this is B part 1. And then for part 2, it says, hence find the age of the car at this instant, giving your answer in years and months to the nearest month. So now we need to solve it. So if we take, we should also put this as, I'll put it down here, 500 then is equal to 3,925 e to the minus 0.25 t. So if we take the 3,000 over to 925 over, we would have then e to the minus 0.25 t, and that is equal to 500 over 3925. Again, we would take logs of both sides, or ln of both sides. So that we would have minus 0.25t equal to ln of 500 over 3925. And again, this is the same as minus a quarter, so t equals minus 4 ln 500 over 3925. So t is equal to 8.24. Now we go back to the question and it says, give your answer in years and months to the nearest month. Well, we know the 8 is in years, but the 0.24, we need to work out what is 0.24. So that's the same as 0.24 times 12, because there's 12 months in a year, and that is equal to 2.88. So then our t is equal to 8 years, 3 months. And then if I put part C over here, and it says the model predicts that the value of the car approaches but does not fall below A. State the value of A. Like the other one, the value of the A is going to be the constant which is on its own in the original equation. So in that case is going to be 2,300. It won't fall below. And then part D is state a limitation of this model. Well, if we think about it in real life, this model is if the car is in perfect working order and nothing happens to it. So what could happen to it? Well, there are other factors that affect the price. The price actually could increase in value because it was less sold or it was made in a particular film or anything like that. So you have to think about it. It could also be that it decreases in value because it's had an accident, there's scratches on it. So those type of things, anything which is relatable to the question, but also is sensible. So I'd probably go for damage to the car. Limitations would be damage to the car and means that the model would fail. Damage to the car from accident, But there is nothing wrong, as I said, in saying that the price increases. You would just have to give a reason why you think it could increase. Right, is exponentials. We covered. So what I'd like to go on to, oh no, I've got one left. No, this was, I threw a log question in just to sort of, for the sketching element of things, especially that y equals kx. So first thing is you have two curves, have the equation y equals ln of x and y equals k over x. K is just a constant. So we know how to sketch ln of x because we did that at the start. So that is going to be like so. And label it y equals ln of x. And then I'm going to go to different color. Then we need to do k of x. Now the k over x, if you know what y equals 1 over x looks like, it's the same thing with k over x. It's just stretched out in the y-axis. But because we're just drawing a sketch, it's acceptable for you to sort of draw it looking there and there. And I'm not a big fan of that one, so let me... No. And then again, label this as y equals k over x. So there's your sketching for 3 marks. And then part B is part A. Explain how your diagram shows the equation x ln x minus k equals 0 has exactly 1 real root. Well, this looks like it's showing that it's 1 real root is a combination of the 2 above. So whenever you're asked for interception of 2 graphs, it is always talking about simultaneous equations. So you know you're going to solve via substitution. So because the y's are equal to the functions, then you would just say, well, ln of x equals k over x. Move the k over to the other side, minus, sorry, move the x up and move the k over. So that's the original equation. Therefore, from diagram, the graphs only cross in one place, therefore it's 1 root. The graphs only cross or intersect, sorry, only cross in one place, therefore only 1 root. And the 1 root is there. Okay, I thought I'd put that in again for the sketching element of things. And then we'll see, yeah, how we're doing for time. I think we've got enough time to go through the transformation curve. Right, so there are 3 different elements of transformations. There is translation, which we're starting with here. After translation, there is reflection, and then it moves on to stretching. It is important that if they ask you to describe it, you use the correct words and phraseology. So here we have a sketch of a graph. We don't know what the graph is. It's just y equals f of x. And it's given us, the diagram above shows the curve with the equation y equals f of x. The curve has a maximum point of minus 2,5 and has an asymptote at y equals 1, as shown in the diagram above. So the first part, on separate graphs, sketch the curve with equations y equals f of x plus 2. So for part A, y equals f of x plus 2. Notice the number is outside of the bracket. So if the number is outside of the bracket, that is what we call a translation of 2 units or plus 2 units in the y-axis. So what that means is the graph moves up 2 units in the y-axis. So when you draw it, your sketch, first thing is the asymptote, instead of being y equals 1, is going to be y equals 3. So you draw your dotted line, put y equal to 3. And then your curve, you don't know where it crosses the y-axis, the x-axis, and you don't know where it crosses the y-axis. And to be honest, you don't really care, because you want to show that it's moved up, which you've done. You've showed that the asymptote was moved up, but then you show that the coordinates of the maximum, instead of being minus 2,5, is now going to be minus 2,7. So everything is moved up, and there's your answer. Now parts, let's do blue. Part B, notice that the number is inside the function itself, inside the brackets. So this time you're going to have a translation. So for y equals f of x plus 1, you're going to have a translation of minus 1 unit in the x-axis. So if it's inside the bracket or inside the function, it moves along the x-axis, but it moves the opposite way that you would expect. Plus goes left in the minus region, minus goes right in the positive region. Whereas for translation in the y-axis, it goes the way it says. Positive moves up, negative moves down. So the let's have a look. The actual asymptote hasn't changed, so you can put that in. So it's going to be y equals 1, and we always use a dotted line. The graph has to have shifted. Again, we don't know where it was on the x-axis, so we just need to sort of put it along. The point now, instead of it being minus 2, 5, is going to be minus 3, 5. So you just need to shift it along on the left. So it would come up, go down, and go there. Don't like that one. It's too close to axes. So it'd come up, down, and go along like so. And then this new point is going to be minus 3, 5. And again, the translation is that movement along the different axes. Next one is reflection. So there are two types of reflection. The first one is the minus sign is multiplied by the whole function. So then this reflection is a reflection in the x-axis. So if we have a y equals minus f of x, minus sign outside, side, reflection in x-axis. So what it means is the x-axis is the mirror line. And again, it's telling us the coordinates on the x-axis, and it is the point of the minima here. So in the diagram where you sketch it, you need to show that movement, and also you need to show those coordinates again. So if we draw our graph looking like so, so we know it crosses at 2, we know it crosses at 4. How it crosses is deflection means it comes up like it did here, goes down, and then goes off. Then that's going to be in that. That's wrong on that side. Let's do that again. So it comes down like so. So it comes from here, going up, down like so. So it comes off as if it's going off for a minima in this case. Notice now, this is why I should never put in the numbers until after you have drawn it, because what I did there was you couldn't see what the numbers look like. So that is a 2, that is a 4, and this is going to be 3, 2. For the next one, I'll change color again. You have y equals f of minus x. That's inside. Part B, y equals f of minus x. That minus sign inside means a reflection in the y-axis. So your y-axis becomes the mirror line, so it's reflected and goes that way. So again, if we draw it, sketch it, so it crosses at 1 and at 4, so it's going to be then minus 1 and minus 4, and the top point is going to be between them. Okay, it's slightly more tilted there, so this will come up, down. This one would be minus 1, minus 4, and then this is minus 2, 5. And the last we have is stretch. Now parallel to the, and then it's dot dot axis. So here we have y equals 2f of x. So because the 2 is outside, outside or number outside, we have a stretch parallel to the y-axis. by a scale factor of 2. So what that means is every y coordinate is multiplied by 2. So when you draw it, your x values don't change. Goes there, goes there, goes there. It just means that it comes from here, goes up higher, down, goes down lower. So this point is going to be minus 2, 6, because the y part was 3, is now doubled. And this one is 3 minus 10, because the y part is doubled. And that's if the number is outside of the bracket. And then the next one, notice the number is inside the bracket again. So if we have y equals f of 2x, number inside the bracket, it would be a stretch parallel to the x-axis by a scale factor of a half. So the number inside, let's put a note, number inside is the scale factor is the reciprocal of it. Scale factor is the reciprocal. Which just means that you would flip. So here, all of the x values, not the y this time, but all of the x values are multiplied by a half. So when we have our graph like so, instead of 2, it's going to be 1. Instead of 4, it's going to be 2. Instead of 3, it's going to be 3 over 2. So it gets a little bit tighter in. So it goes down, up, goes off. So then this point is 1, this point is 2, and then this point is going to be 3 over 2 minus 2. Like so. So it stretches in like that. If it was f over half x, then the scale inside the bracket, then the scale factor would be a factor of 2. Right, I've got, times it, I've got 3 minutes, which will be fine because I've got 3 questions, which will be a minute a question. So here it says sketch a graph of y equals minus 3 f of x. So the minus is outside. So if we put minus, so y equals minus 3f of x. The minus is a reflection in x-axis because it's outside, and the 3 is a stretch. So to what was it? 3 is outside y-axis. So first of all, I would probably flip it. And then once you flipped it, you're going to multiply all of the y values by a factor of 3. So it's going to be down like so. It's still going to cross at minus 4 and 6. But this time, the maxima is going to be up here somewhere. So instead of it being going to be more looking like so. So this is at minus 4. This is going to be at 6. And then this is going to be 1. And then, sorry, not 1, minus. That'll be at 1, 9. That'll be at 1, 9. Now, I have got 2 more questions, but what I'll do is I will put them on the website. I'll just finish them off quickly now, and I'll put the resources in. And I will hand you back to Mr. Weatherhead. Thank you, Mr. Weatherhead.
Thank you, Mr. Mackenzie. Hopefully you found today's session useful. Okay, remember the video and all the resources will be on the e-sgol website. Your final one for AS Maths next Thursday will be with me. We'll be looking at some mechanics, looking at forces and pulleys. So hopefully we will see you then. Thank you very much.